We will briefly talk about the application of quantum mechanics to trying to solve the equation of motion for hydrogen. That's called the solutions of the Schrodinger equation. And just using all those terms, it may be a little bit overwhelming. The scope of this section is not for you to quite understand the mathematics of the whole process, but just to understand what the Schrodinger equation is, what solutions come out of the Schrodinger equation, which is the atomic orbitals, when that equation is applied to the hydrogen atom. First of all, what's an equation of motion? Quite often, in outside of a certain level of chemistry, you may see atoms portrayed, again, something that we even ourselves have been using, as this picture of electrons like planets orbiting around the nucleus. However, that's not quite accurate, mostly when one applies the quantum mechanics to atomic systems. So an equation of motion tells you where your particle is at a given point in time, or in this case, if your particle is not a particle but it's a wave, like a wave of probability, like an electron, it will tell you how that wave of electron is distributed. Uh, if you have taken physics, probably you're familiar with the equation of motion of a stone being thrown. The position of the stone depends on the initial position plus the velocity times time plus the 1/2 of the acceleration times time square. This is a very simple equation of motion. The equation of motion for the electron inside the hydrogen atom may be a little bit more sophisticated, but it tries to answer the same question. Where is the electron? Okay, and this is what the Schrodinger equation is. It's just applying wave mechanics and using the Heisenberg uncertainty principle. This combination, Heisenberg uncertainty principle and wave mechanics, is what Erwin Schrödinger did in 1926, and he was able to come up with the solution of this differential equation, which is, as we said, the atomic orbitals. Okay, so the atomic orbitals look like that. Look like a function that has three main parts. It has a part that is what we call the radial part, that talks about the size of the orbital, and it has an angular part that talks about the shape and orientation. All right, so this is what an orbital looks like from the mathematical point of view. And if you like a graphical display of the orbital, this would be what a 3s orbital looks like. Notice it's a wave. It's a static wave. The wave does not change through time in the sense that the distribution of the electronic probability is constant through time. So let's look a little bit in more detail. What are the shapes of the atomic orbitals? Again, atomic orbitals will be this wave of probability of electrons. The s orbitals, here you can see the 1s, the 2s, and the 3s, and in here what you can see, it's what's called the radial distribution. What's a radial distribution? So if you think the atomic orbital as if it were a cake, what the radial distribution does, it slices the cake and it tries to see, so this would be the slice of the cake, so this would be the center and this would be the outside of the orbital. It tries to see how the density of electron is distributed in the atom. We need to introduce a concept called nodes. A node is a plane, a point in the orbital in which the probability is 0, in which the value of the function is 0. Typically, it will go from negative to positive. And notice that in the 2s, there is, probably the color red is not the most appropriate, you may see that there is this circle in which the value of the function is always 0. So we will say that the atomic orbital 2s has one node. And the 3s, if you can see it, there is an inner circle and an outer circle in which, so it means that there is two nodes that this specific orbital has. Now, Let's look at the p orbitals. In the p orbitals, notice that at the center of the orbital, the probability of finding the electron is 0. So the value of the function is 0. So the 2p already has one node. And in the 3p, with some imagination, you should be able to see, probably using the radial distribution function, maybe easier, you see two nodes. So hopefully you're seeing a pattern here. The number of nodes is always what we call n minus 1. What's n? N is this so-called principal number, principal quantum number. So a 3s, a 3p, a 3d will have two nodes. A 4s, 4p, and 4d will have 4 minus 1, 3 nodes. Okay, and the nodes are important to identify them because it will mean that there is zero probability to find the electron there. That means it's not available for combining with other atoms and making chemical bonds. Finally, let's just look at the 3D and 4D and 5D, the d orbitals. Notice that it gets more difficult to represent, and any kind of representation, because it's a function that's spreads in the 3D space, in the three directions of the space, it's hard to represent, and so these functions are fairly complex, but we may want to look at the shape and also the number of nodes.